Hello everyone and welcome to this video. Today we are going to hear from the Tridora CPU because I have been working on audio capabilities. I have had this extension board, that is the Gitlab AMP2P mod, lying around for quite some time now. Now I have finally connected it to my FPGA board, and it has a 3.5mm audio jack in mono that is connected to the speaker here. And it also has an audio amplifier chip on it that has one analog input pin, and that is connected to one of the FPGA output pins. Now, the simplest thing to do to get some sound would be to send alternating ones and zeros to that output pin at a certain frequency in the audible range. And then you would have something like the PC speaker, a pulse wave or rectangle wave at maximum amplitude, where you can control the pitch of the tone. But that's a bit boring, so I wanted to do something more sophisticated. So I made an audio controller, much like the sound generator chips that many home computers or even arcade machines of the early 1980s had. Here is a diagram of the design I made. There are 4 channels which can generate a pulse wave, controlled by a clock divider, and you can also set the amplitude of the pulse wave. We'll go back to the rest of the diagram in a moment, but for now let's hear how this sounds. I have a small assembly language program here that pokes the registers of the audio controller to create some sound, and it sounds like this. In the first part there were some tones which got softer at the end, so an amplitude envelope, and this is done in software. But how do you get a lower amplitude if you only have one digital output pin? So that's where the right hand side of my diagram comes in. There we have a digital analog converter that creates a 1-bit output at a frequency much higher than the original audio signal. And this is called pulse density modulation, and it creates a high density of pulses in a certain time frame for a high amplitude and a low density of pulses for a low amplitude. This is like dithering a grayscale image to show it on a monochrome display. And this is also called a Delta-Sigma-DAC. And the mathematics behind this are non-trivial, but the implementation is quite simple. You have an accumulator where you just add the amplitude values, and whenever the accumulator overflows, you output a pulse to the analog amplifier. So this is what allows us to control the amplitude of a channel and also to actually mix the channels to get one combined audio signal. So that's great, but still kind of boring, isn't it? So I also implemented a feature where you can turn off the pulse wave generator and control the amplitude value directly by writing to a register. If you do that fast enough, you can have sample playback driven entirely by the CPU. So I tested that and it worked well, and then I thought, let's scrap that pulse wave stuff and just go for sample playback. So I removed the pulse wave generator and added a sample buffer for each channel that is organized as a 16-slot FIFO. And I also wired up the audio controller to the interrupt controller, so you can get an interrupt whenever the sample buffer is empty. This way you can have interrupt-driven sample playback where your program continues to run normally while your sound is playing in the background. And it still uses some CPU time. At 32 kHz it uses about 7% CPU power for one channel. So let's hear it. I have a little demo program here. Let's have a quick look at the source code. I'm using a small library I wrote for this, and yeah, here we have a function that reads the sound file, nothing really special about it. And here is the main program. Here we read the file and start the sample playback with this procedure. Then comes some kind of main loop where you can type something and you can press escape to exit, or you can press a question mark to show the sample queue status. And if the main loop exits, then we just stop the sample playback. And that's it. Very simple API. So let's exit the editor, and I have compiled the program already, so we can just run it. Now I have to enter the file name, and then it reads the file. And as you can see, this takes quite a while, because this is a 30 seconds clip. And at 32 kilohertz in 16-bit mono, this is a 2 megabyte file. And while this is not a real problem for the Tridora CPU, it is still quite a bit of work. And since we are a retro computing project, this is about 1.5 high-density floppy disks worth of data that we're reading in here. The audio coming from the Tridora CPU is being recorded with this portable digital recorder that's sitting in front of the speaker, my trusty old H2N. And this will result in a much better recording than just using the camera microphone. And when the sample playback starts, I will type some nonsense so you can see that the program continues normally. And that's it. Interrupt-driven sample playback on the Tridora CPU. Now, that sounds really a lot better than the 4-voice beeper, doesn't it? And that's all for today. Thank you for watching, have a nice day, and see you in the next video.